you that just like to go watch this a second time because it was so much fun. Yeah,
Did you say that? I hit the subscribe button.
Yeah.
If you hit start, if you say smash that like button,
If you don't know how to pray, hit that follow button.
or you do pass it to be like, I don't really care.
Yeah. Yeah. Okay. This one's on my school account. I'm pretty sure I can't monetize it. I need to have my own separate one if I want to monetize, I think. Yeah. Okay. Yeah. Yeah. I mean, these are all really good ideas that I think could be done well and be successful, actually, but I've not got time to become a calculus influencer. So I gotta take a break in the summer. This summer I got a lot of stuff going on too. Definitely don't have time. All right. Okay. For this one, that 3x right there is going to be our u. So du is just going to be 3 dx. All right. Is my music playing? Seems like it's on that side. Maybe it's out there, yeah. Okay. So I have my dx, but I don't have a 3 with it, so I need to multiply by 3 here. And if I squeeze that 3 right there, what have I got to do on the outside? 1/3. Right, and that balances out because 1/3 times 3 equals 1. We haven't actually changed the value of anything. So this stuff right here is my du. So I can substitute in my u's. I'll have 1/3 the integral of sine u du. Okay. What do I get when I integrate sine? Negative cosine. When you're integrating, it's going to be negative. When you take the derivative, it is positive. So I'm going to just go ahead and put it out in front of the 1/3. So negative 1/3 cosine u plus c. And then I want to plug in the u. So I'll get negative 1/3 cosine of 3x plus c. And that would be my answer. Okay, questions? All right, let's try this next one. All right, so we got sine of 5x times cosine of 5x dx. So this one becomes a little bit more difficult to figure out what the u should be for this problem. What do you guys think? Okay, cosine, just cosine or cosine of 5x? Okay. You might be thinking maybe it should be 5x, but if it's 5x, then we got sine u, cosine u. Do we know how to integrate sine times cosine? We do not. So let's go with that cosine of 5x. Let's try that. So u equals cosine of 5x. So if we take the derivative of that, what's the derivative of cosine? What kind of sine? Negative sine, because we're taking the derivative here. So it's going to be negative sine of 5x times 5, because that's a chain rule that we have to use there, and then we'll have dx out here. So let's clean that up a little bit. It's going to be negative 5 sine of 5x dx. Do we have negative 5 sine 5x dx? We got sine of 5x, so the only thing we're missing is the negative 5, and that's okay because we can add in a multiply in a coefficient, right? So we could put a negative 5 here. Negative 5 right there, as long as we put what on the outside? Negative 1/5. Right? So I'm just going, gosh. I'm just going to do this stuff right here. There's my du, right? And so if I translate this over to my u's, I will have negative 1/5 integral. And then this is just u du. Everybody okay here? All right, that's like u to the first power, so we need to integrate this. It's just the power rule. We're going to go u to the second. We got to divide out front by that 2, so we'll get a 1/2. We still got that negative 1/5 that's out there as well. And what else do I need? Plus c. And so I will have negative 1/10. And then I'll have cosine of 5x squared. That will probably be written this way. Cosine squared of 5x. Like that. Now, there's a chance that you may do this problem, and you may get to the end, and that's not the answer choice that is there. Because, did our u have to be cosine 5x? It could have been sine 5x, because what is the derivative of sine 5x? It'll be positive cosine, well, it'll be 5 cosine 5x, right? So, we could have, in this particular case, a lot of times this is not the case. Usually there's only one thing you can pick for your u, and then it'll work. Because sine and cosine are derivatives of each other, you could pick either one. You could have used sine as your u instead of cosine. And so if you did that, you would get like a positive 1/10 sine squared of 5x plus c. It ends up being an equivalent graph there. You could use trig identities to get it to match. So definitely if you're doing this problem, you may want to look ahead to your answer choices to kind of see where everything's sine or cosine, because that would affect what you put for your u for that. Yeah, if all your answers have sine in them instead of cosine, make sine your u instead of cosine. They might, because they are evil geniuses. They would never have two correct answers, though. So they would not have the correct sine answer and the correct cosine answer. Every once in a while they do things like that, where they've got one of each, and that does make it difficult, because maybe you choose cosine and then your answer is not there. So you were supposed to choose sine, but there was no like indication that that was the case in the first place. So it could happen. Okay, questions? All right, what about this next one? Oh. Yeah, just go ahead and copy down the problem, go to the back of the book, write down the answer, skip on ahead. It's possible that I think that we're capable though. I think we can do this. But, now, is this one where it does not matter what you choose for your u? No, because is the derivative of tangent secant and the derivative of secant tangent? Is not. They're related, but they're not the same. Which one of these could we take the derivative of and it will give us the other? Tangent. What is the derivative of tangent? Secant squared, right? So you may even want to think about it like this. This is really tangent of 3x to the third power times secant squared 3x dx. So if I take the derivative of tangent, if I let this right here be my u, I'm going to get a secant squared for that. So u, in this case, is going to be tangent of 3x. Du is secant squared 3x times what? Times 3, because you have to use a chain rule there, and then we'll have a dx beside it. Do I have what I need for my du? Need a 3, right? So if I put a 3 right here, excuse me, I will also have to put a 1/3 out front. But now all this stuff right here is my du. We okay here? All right, so let's convert this to u's. We got 1/3 integral u to the third power du. I'm going to integrate that u to the third, so I'll do u to the fourth. I got to divide out front by that fourth, and that 1/3 is still out there as well. And what else do I need? Plus c. So I'm going to get 1/12, and then I can plug my u back in if I want here. Tangent of 3x to the fourth power plus c. It's probably more likely to be written this way. 1/12 tangent. I'll put the fourth power right here of 3x plus c. Questions? All right, here's a new trick one. Let's do that. Let's write this as the integral of, and I'm going to write this way, tangent x to the -4 power times secant squared x dx. So, what should I use for my u here? Tangent again. This time because I got that secant squared, right? So u is going to be tangent of x. The derivative of tangent is just secant squared x dx. Do I have my du? Yes, I've already got it. I don't even have to add anything in this time. This stuff right here is my du. Everybody good here? All right, so we're going to have the integral of u to the -4th du. So that's going to be u to the -3rd, and then I have to divide out front by that -3. I'll put the plus c on the end. So I will get -1/3 tangent of x to the -3 plus c. There is a good chance they're going to put that back on the bottom So it'll be like negative 1 over 3 tangent cubed x plus c. Definitely, free response, you can stop here, leave negative exponents, it doesn't matter, but a lot of times for multiple choice, which is where you see these a lot, you're going to have this. Okay, questions? Okay. Okay. All right, here's our next one. All right, so what do you guys think for the u for this one? 3x minus 2. All right. So u would be 3x minus 2. Du then is just 3 dx. So we don't have the 3 with our dx, but we can multiply that in right there very easily as long as we put our 1/3 out front. So here is our du. So to convert that to our u's, we're going to have 1/3 the integral of 1 over u du. What is the integral of 1 over u? It's natural log. And it's sneaky because this looks nothing like a natural log, right? Like it just sneaks right in there. But if you try to do this with negative exponents, you got u to the negative 1. And if you're trying to integrate u to the negative 1, you would increase your exponent by 1. It would be 0. Then what would you have to do with that 0? Divide by 0. Can you divide by 0? No. So if you find yourself trying that and you're having to divide by 0, that should be your alert that this should be a natural log, right? So this is natural log. Whenever we integrate it, we're going to get 1/3 natural log of the absolute value of u plus c. We have to have those absolute value bars because whenever we are taking the natural log of something, it must be a positive number. So we need those absolute value bars. So our answer would end up being 1/3 natural log absolute value of 3x minus 2 plus c. Now, these are not, I mean, there's some of the easier ones really to do most of the time, but one of two things usually happens. Either you start doing natural log for anything that's a fraction, right? If I got 1 over 3x minus 2 squared, is that a natural log integral? It is not, because it's to the second power. I can do negative 2 exponents, right? So that would not be a natural log. Either kids start doing natural log anytime there's a fraction, or they still can't remember that you need to do a natural log on these problems. If you remember what to do, they're not that bad, but they're tricky on recognizing them as natural logs for that. All right, let's try this one. If you tried to get rid of some of those x's, what would you do? No. Yeah, it's subtractive. If it was multiplied, you could, but if you did try to do something like that on this, like if you were trying to love connection this, can you do that? You cannot do an upside down love connection. So it is not allowed at all. You'll hurt yourself. Don't try it. Yeah, so you have to be dividing your numerator by your denominator. Huh? You can do triple, double, quadruple. Yeah, the number of terms on the top for a love connection does not matter. But do not do it upside down. It can be more than 1 on the bottom. It's just usually not helpful. Like, for example, if I had x squared plus 4 over x squared minus 2, I could write it as x squared over x squared minus 2 plus 4 over x squared minus 2. Like, you could do a love connection like this, but you can't split up that denominator there. And usually that's not helpful to do, so we don't usually. Yeah, it would actually make it like more complicated. So the time we usually use the love connection is whenever we only have 1 term on the bottom for that. So we cannot love connection this. It'd be an upside down love connection. It would not end well if we tried that. So we then are probably going to have to do a U du. What should we use as our U? The bottom. Because if I use x squared, the derivative of x squared is just 2x, and I'm not going to be able to do anything with that x cubed, right? But if I make this my U, then U equals x cubed minus 8, so du is going to be 3x squared dx, and I do have an x squared, right? Now, I need that x squared to kind of be over here with my dx, and I need a 3 with it. If I put a 3 here with this, I got to put a 1/3 out front. And so we can kind of think about this. I'm going to rewrite this way. I'm going to write this as 1 over x to the 3rd minus 8 times 3x squared dx. Is that equivalent? Like if I multiplied that back together, I could put this over 1 and I'd get the same thing I started with, right? That just helps me see where everything goes a little bit better. This is my u. This is my du here. So to switch to u's, I'm going to have 1/3 integral of 1 over u du. What is the integral of 1 over u du? Natural log of the absolute value of u. Perfect. So 1/3 natural log absolute value of u plus c. And so we will get 1/3 natural log absolute value of x to the 3rd minus 8 plus c. Not so much. These usually end up on like the naked problems with no context. Usually. I guess they could. Alright, look at this one. What should you be for this one? If x is our u du is just dx, right? What are we going to do with that natural log to the third on the top? You cannot just throw it away.
Drop a log.
You cannot just drop the log. I saw him at the shooting team Saturday. Asked him how it was going. He said it was same as Elkin. Kids are the same, he said. Now, that's probably true for him. What I would like to know is what the kids think about Coach Wood.
Yeah.
Because
Not the same.
that's not the same, I'm sure. He might. Here's what I wonder. Yeah, here's what I wonder. Are they calling him Coach Wood? Because he's not coaching anything. Are they calling him Mr. Wood?
No. Miss Brown always called him Mr. Wood, and it just threw me off.
Yeah. Like, I still have to call Coach Foster, and he hasn't coached anything in a long time. But calling Coach Wood Mr. Wood is not. Surely they're calling him Coach. Like, you can kind of just look at him and say he obviously is a Coach Wood. Like, you don't. I don't know. It is. Okay. All right. What we're going to have to do for this one is natural log is going to be our u. So if I take the derivative of natural log, what is it? It is 1 over x with a dx. Now, can I pull this apart? Can I make this natural log of x to the third power times 1 over x dx? Is that okay? Because, like, this would be over 1, right? And if I multiplied it back together, I'd have what I started with. So I'm just kind of like pulling that apart. So this piece right here can be my u. This piece right here is my du. I don't even have to add any numbers in on this one. So when I switch this over to u's, I'm just replacing everything with u's. So I've got an integral. This stuff in the box right here is u, and then it's to the third power. And then all the stuff in the screen box is my du. Everybody good there? So we will have u to the fourth. We'll have 1/4 out front plus c on the end. And so that will be 1/4 natural log of x to the fourth power plus c. All right. Well, do I have time for that? The e's are fast. We can, yeah. Okay, here's 8. What's this the derivative, or what's this the integral of? This is tangent, right? So what we're doing right here is we're finding the integral of tangent, because we don't know how to find the integral of tangent with like a rule, right? We could find the integral of secant squared or secant x tangent x, but when we take the derivative of tangent, we get secant squared x. So we can't go backwards from tangent. So to do the integral of tangent, it's a more complicated process. It's not just a rule that we have memorized. So what are you guys thinking here for our u? Okay? Cosine is going to be our best bet. Now, sine is the derivative of, like, they're the derivatives of each other, like that earlier problem that we did, right? Is it okay to use either one on this one, though? It will not be, because this cosine right here is in the bottom of our fraction. And we need to have whatever our du is needs to be in the top. It can't come from the bottom there. So we need to use the bottom. We're actually going to see a natural log show up in this, which is kind of crazy. It's like weird that it ends up, to me it's kind of like, it's kind of cool though, how you can integrate tangent and a natural log, which seems to be totally unrelated to trig, just shows up in there. Math is kind of cool how it's like all connected together. All right, so if I take the derivative of cosine, what do I get? Negative sine of theta d theta. So let's think about this. Let's pull this apart so that we can see it a little better. This is 1 over cosine theta times sine theta d theta. That is equivalent to what we started with. We're just pulling it apart so we can see our two pieces separately. And we need a -1 over here so that we have our du, which means we need to multiply by a -1 out front as well. So that denominator there is our u. All of this stuff over here is our du. And so when we substitute in, we've got 1 over u du. What is the integral of 1 over u? Natural log. So we got negative natural log absolute value of u plus c. And then we are going to plug in our u, which was cosine of theta plus c. So the integral of tangent is negative natural log of the absolute value of cosine of theta plus c. Yeah. Yeah. Well, it does look like. Maybe you should make your L curly there. Yeah. How did I figure it out? I can't answer you for how they figured it out. It's a little beyond. This would be, now, this is your general integral, right? But your integral gives you the area under the curve. However, like this is just general. We could use it for a definite integral because like we would have to know from where to find that area under the curve. But this will be general, and then if you were figuring it from like 0 to 7, then we'd have 0 and 7 here, and we plug those numbers in. It also works like, let's say tangent of theta was our velocity, right? When we integrate, it gets us back up to like our position formula there. Yeah. And if you wanted to know like position at time 7, you would plug in 7 for that. Yeah. Not quite. We'll look at that. We'll look at that more in the next section. All right. Okay. E's should go fast. We got a few that with e's they should go very fast because e's are going to be your easiest ones. Because what is the derivative of e? E to the x. And then what is the integral of e to the x? E to the x, right? So these are just like teeny u substitution problems. They're so tiny that it almost feels like you're not doing u substitution. If you have an e problem, typically the exponent is your u. Unless it's maybe like a really complicated something. Exponent would be u. So u would be 3x. What would du be for this? 3 dx. So we do need a 3 over here with our dx. What have we got to put out front? 1/3. So our exponent, our u, is our exponent here. This part right here is our du. Okay, there. All right, so we got 1/3 the integral of e to the u du. What do we get when we integrate e to the u? E to the u. And then we'll have plus c. And then we just plug back in our u. So 1/3 e to the 3x plus c. Sometimes students, when they do this, they do most of that in their head and they don't write it all down. That's fine as long as you're getting the right answer. I like to organize. Yeah. Yeah, you're probably okay for doing that. They're usually not going to ask you to show the steps. Okay, questions there? Let's see. All right, let's look at this one. Now this one's got a little bit more going on. We got 5x e to the x squared dx. But we got that e to a power. It's probably still going to be the case that this is my u. And what's the derivative of x squared? 2x. So it would have an x to the first power. So this is going to be the way to go. So u is x squared. Du is going to be 2x dx. All right, so I need a 2x dx. But what have I got? I got 5. And 5 is in my way because I want a 2 instead. So I prefer, you can multiply that by 2/5 if you want. I prefer to just get the 5 out of the way. I pull it out here, and I take my x, I put it over here with my dx so that it looks like this. 5 integral of e to the x squared times x dx. And then I need a 2 to go right here with that x, so I will multiply by 1/2 on the outside. Now, essentially what I'm doing is I'm multiplying by 2/5 on the inside and 5/2 on the outside, but you can definitely think of it that way as well. But for me, it's just easier to separate them out there. So this is my u. This stuff right here is my du. Right here. All right, we'll have 5/2 integral e to the u du. What do we get when we integrate e to the u? E to the u. So we'll have 5/2 e to the u plus c, and that will be 5/2 e to the x squared plus c. Make it 10. No. Not on this one, no. You would have, because you got to have the 2x. What you could do, Liam, instead, you could think of it as multiplying this by 2/5, right? Because 2/5 times 5 would give me 2. And then if I do that, I got to multiply out here by 5/2. So you can think of it that way. But it should still be those same numbers there. You end up with either way for that. All right, last one. That was 10. Don't let it happen again. Oh. All right. There are 2 e to the x's this time. So since this has happened, we can't use 3x as our u, because then du is just 3dx, and then we have an e to the x in the top, or e to the u in the top and an e to the u in the bottom, and we don't know what to do with that. That's too complicated. So what else do you think we could try? Let's use the denominator. When in doubt, use the denominator, and maybe this is a natural log problem, right? So u is 1 plus e to the 3x. Oh, I'll put the x down here. 3x. All right, what is the derivative of 1e to the 3x? It is 3e to the 3x dx. Now, we already have e to the 3x. It's in the numerator where we want it. We just need the 3 with it. And then that means we have to have a 1/3 out front. Okay? So, we got 1/3. Let's separate this actually, just so we can really plainly see. We got 1 over 1 plus e to the 3x times 3e to 3x dx. So this part right here is my u. This part right here is my du. So we got 1/3 1 over u du. What is the integral of 1 over u? Natural log of the absolute value of u plus c. So we got 1/3 natural log absolute value of 1 plus e to the 3x. They would cancel each other out if we did not have that 1 right there. Because of the 1, they're not going to cancel each other out. If our u had just been e to the 3x, then they would cancel it out, and we would just have a 3. Now, you might see this answer written this way. Is that okay? It is. Why? Why is that okay to do here? Right, that can't be negative because 1's positive. Exponential is always positive. You're adding 2 positive things together. So they sometimes will drop the absolute value bars whenever they're unnecessary. Now, on everything else we did, they were necessary because you could get a negative in there. All right, now let me look because I have like a crazy assignment that comes from different sections, and we're going to shorten that. I don't know why I ever assigned so many at one time. Surely I didn't do that to everybody. First, let's go to Canvas and see if it's different there.
You must have not liked the group.
Maybe we did it like over a couple days. Maybe, I'm not sure. I promise we're cutting this down. This is like at Belk's when it says the sweater's $79.99, but it's really 85% off. I'm trying to make you feel better about your homework assignment, maybe. All right. Oh, I got to go to the right. I know. Surely I didn't do that to kids. And I didn't. I'm getting soft if I used to give this. Okay, let's see what this says. I think that was the old textbook. Okay, this seems like a more reasonable assignment right here. And I might even, since we don't have any work time, I might even cut a couple off of those. Let me look at what we've got. Yeah, I think this is the old textbook. I think that's the old textbook book numbers anyway, so it's not that one. All right, 341, 31, 345, odd. Let's do page 341. Let's do 33 through 43 odd. That's going to have your trig and your E stuff in it. And then to get the natural log stuff, we got to go to 351. Sorry, we got to do some of that too, though. We'll do 3 through 11 odd. 3 through 11 odd.
3 to 4 even.
Look what it could have been, guys. Look what it could have been.
It doesn't make it any better.
3 to 3
It could have been that.